Okay, so this video is going to go over lesson 4, translating logarithmic functions. So for the warm-up, what I'd like you to do is take a couple of minutes to think about the 4 log equations given and think about what you already know about the transformations of functions. We've looked at properties of transformations this year with other functions prior to logarithms, and see if you can write in words what's happening to the original function log x if we, for part A, it says log x plus 3. What is that plus 3 doing to the original function that's highlighted? Pause the video, take a minute or two to try each one, and then we'll go over it. Okay, so if we review just transformations, when we have a function and any value is being added or subtracted outside of the function, that value, when it's positive, means our function is being shifted up that many units. And if that value happened to be negative, then our function is shifting down that many units. So for part A and B, that's what we're looking at, a vertical shift. So for part A, the log graph is shifted up 3 units. And for part B, the log graph is being shifted down 3 units. You could also confirm this by plotting these in your calculator and looking at the graphs. We can do that at the end to confirm. Now, when you have a value inside of a function, let's say we had something like this, that value, the horizontal shift, is when things are opposite as they appear. So when you see a positive value inside, it actually means your function is shifting to the left h units. And when you see a negative value inside, it means our function is shifting to the right h units. So for part C, this would be a log graph that has shifted left 3 units. Again, we see a plus sign, we think opposite. Opposite for horizontal, plus would be left 3 units. Opposite for a negative 3 would mean we're going to the right 3 units. So all of these log graphs are log base 10 because they do not indicate the base. So if we go to our calculator, let's just plot log of x. And then let's even take choice 1. So we had log of x, close parenthesis, plus 3. So you can see my original function is in blue, and the other function went up. If I went here and made this into a negative 3, then you can see the red graph went down from the original. Now let's go back and go inside with x. Choice C was the positive 3. You can see the red graph went left of the original. And then we could do the same thing with the last choice. Choice D is where it went to the right. So you could have confirmed and answered this question with your calculator as well. Okay, so today we're going to take a look at log graphs, properties of them. Let's take a look at exercise 1. So we have the x value of which function's x-intercept is larger. So we're looking for which one has a larger x-intercept. Is it function f or function h? So I see function f is here. Function h is the one given to me in the table. It does say to justify. Just to remind ourselves what that means. That means we're going to just show our math. Let's also review. Okay, so for x-intercept, if we are crossing the x-axis, that means y is equal to 0. So that would mean for h of x is equal to 0. We're looking for what that x value is. Same thing here. If f of x is equal to 0, what x value is, creating the y to become 0. So in the table, we can just find it. When is h of x equal to 0? I can see it down here when x is equal to 2. So h of x has an x-intercept of 2. So now we need to decide if f has a bigger or smaller x-intercept. So one way is just, let's go to the calculator and get a table for f. So let's go to our y equals. We're going to type in, again, this is a common logarithm, so log base 10. We can use the log key right on the front of our calculator. X minus 4. Let's hit second graph, go to the table. And we're looking here, I'm just going to bring this down a bit, and we can see here from the table that when x is 5, y is 0. So to justify this, I'm just going to make myself a table. I'm just going to say 5 and 0. There's my justification. So this x-intercept is 5. The other table had an x-intercept of 2. So my justification is there. I'm showing a table for f. And I'm going to state that f of x has the larger x-intercept. So that would be enough to get full credit on this question. I am going to show you one other way to do this. You did not have to do it this way, but just to show you there's more than one way to do that. Let's say you didn't think to go to the calculator. We know that an x-intercept means y is 0, so if I take this equation and set it equal to 0, I could solve for x. Now how do I solve this? Well, I would use my loop trick. So I really need to think about two things here. I would need to put in the base of 10 so that I can use the loop trick. Now let's circle the base. Let's convert this to exponential form so we can solve for x. Not sure what color I was using. I think it was this one. Okay, so I would get the exponential equation 10, base 10 to the 0 power is equal to x minus 4. Well, what is 10 to the 0? That's just going to be 1. And then if I solve for x by adding over the 4, I also get 5. So this is not necessary. Let me stress to you, you would not have needed to show your work this way. This is just another way. I do think just going to your calculator and writing that 1 point down in the table is quicker, but both of them would be a good justification. Okay, let's take a look at exercise 2. So for this one, we are given two functions. One is a rational function, g of x, 2 over x plus 2. The other one is h of x, which is a log function. It says they're both being graphed on the same set of axes. Which coordinates would best approximate their point of intersection? So let's go right into the calculator. We're going to put g of x into our y1 and h of x into our y2. It doesn't matter which one goes in which. Just make sure you get one equation into one of your y equals and the other into the other y equals. So maybe I'll do alpha y equals enter, 2 over x plus 2. And then we have, again, a common log, so I don't need anything to change that base of 10, log of x plus 1, and then close parentheses outside plus 3. So I have my two functions in my y equals. Let's click graph. Okay, I can see the point of intersection, so let's go to second trace. Choice 5 is my intersect. Again, this is not the 89, so this is a little bit not as nice to use. Why is this one not? Okay, there we go. So it is asking me left bound, right bound. You should end up with that intersection, which is in like purple here, the negative 0.9269, comma 1.863. So I'm just going to write that over here. So the intersection again was an x of negative 0.92692006, just to get all the values, and the y given was 1.863795. Okay, and then it says which one would best approximate. So obviously all of these choices are slightly rounded. So when I look at choice 3 and 4, they do not have the correct values. So let's get rid of those. Choice 1 and 2 both look close. They both correctly round the x to negative 0.9. So when I look at the y, if I also try to round that to the nearest tenth, that should be 1.9, not 1.8. So choice 2. 1 is just a rounding error. Okay, let's take a look at example 3. So for example 3, it gives us the graph of y equals log base 2 of x, and it's telling us it's being translated. Okay, so it's being translated to the right 1 unit and down 1 unit. it's asking us what are the coordinates of the x-intercept of the translated graph. So x-intercept of this new graph. So let's write this equation. So if we are going horizontal, that is happening inside of our function. So that's going to happen with x. We're going to the right 1 unit. You would think positive, but horizontal is always opposite. So that's going to have a -1 inside. And then down 1 unit, that's a vertical shift. That will exactly follow the sign. So that would also be a -1. Now we could just go to our calculator and we could find that. So log base 2, and that's a good idea to practice this one because we haven't done a change of base yet. So let's go to our y equals. Alpha window is the shortcut to get you to log base, which should be choice 5. I'm going to make the base 2. Then in the input to my log, I'm going to type in x minus 1, and then outside another -1. Let's just go to the table, and we're looking again for the x-intercept. So we're looking for what x is equal to when y is equal to 0, and I see that here at a value of 3. So let's come back here, and I can see that point at choice 4. Okay, and the last question we're going to tackle today in our notes is number 4. We're going to graph our own log graph. And this part here, so they give us a function, log base 2 of x plus 3 minus 5. So there's some transformations happening on the parent function of the logarithm. And it says to use an appropriate scale to include both intercepts, meaning x and y. Now, our traditional, just our parent function of a logarithm, just to kind of review what we did on day, I guess, 3. Log functions that are not transformed do go through the point 1, 0, and they have an asymptote that is the y-axis, so they don't actually have a y-intercept. But this log function is being shifted 3 to the left and 5 down. So if it's going to be shifted 3 left and 5 down, this graph is actually now going to come in contact with that y-axis. So instead of having a vertical asymptote, that's the y-axis or the line x equals 0, it's actually going to end up having a vertical asymptote at the line x equals -3, since that asymptote is also being shifted 3 to the left. Okay, but we'll get to that with the table. So that's why it says both intercepts. So we are going to have an x, so this is just the parent function. This is the non-shifted log graph. This would be if it was just like log base 2 of x equal to y. Okay, the other thing is they're asking us to use an appropriate scale, which is an indicator that we're probably not going to be able to just go over by 1 or maybe up by 1 or down by 1. So they're giving us a little hint there. So let's go get this typed into our calculator. So again, alpha window, because we're going to need to put in a base of 2, choice 5, base 2 logarithm of x plus 3, and then -5. Let's go to our table. Okay, and I'm just gonna, we already talked about the fact that the vertical asymptote is at -3. You can kind of see that here because the graph stops having domain values when you see the error happening at -3. So I'm just gonna write down some of these nice points. So I'm gonna start making a table on my notes paper with all these integer points. And I wanna make note that when x is 0, y is the y-intercept. So I've located one of the intercepts, but I also need the y-intercept, which means, I also need the x-intercept. So here is my y-intercept. When x equals 0, y, and I'm sorry if I said that backwards before. Here is my y-intercept. X is equal to 0, so y is equal to -3.4 approximately. Now I need to find the x-intercept when y is 0. So I am going to make a table in a moment with all the nice points, but also this one because this is an intercept. That's important to note. So I'll put, 5, -2, and 13, -1. But we need to figure out when does y become 0. Keep scrolling, keep scrolling. Oh, okay, I found it. 29. So the x-intercept is 29. So I'm clearly not going to be able to count over on my x-axis by 1, unless, of course, I have 30 boxes, which I'm pretty sure we do not. Let's see. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 boxes. So if I need to count at least to an x-intercept of 29, I need to at least go over by 3s, because then I could fit up to 30, right? So I'm going to, first let's make our table. I'm just going to write out the points here. So again, you would be making this looking at your calculator. I wrote these down so that I didn't forget them already, and I will transcribe them here. So all of the nice integer points and my intercept. So -2, -5, -1, -4. That y-intercept was that -3.415 approximately. Again, all the other points I'm writing down are just the ones that were nice integers until we got out to that last value we needed, which was the x-intercept. So here are my intercepts. These are the points I had to include because the question told me to. And the other points will just kind of help me make a nice graph. Now, the y values, I can count by ones on my y-axis because I'm only going, as low as -5 as really as high as 0. On my x-axis, though, that's where I need to count by at least 3. So I'm going to count by 3. So this will be 3, 6, 9, 12, 15, 21, 27, and 30. And then -3 is actually, right? We said this graph was being shifted 3 to the left. So the x equaling -3 is the vertical asymptote. Not that you have to draw that in, but I'm going to actually draw it in with just the highlighter to remind myself that this is what my graph's never going to touch. Again, you do not have to draw this. I'm just going to give myself that guide so I know not to plot on or to the left of that line. Okay, so now let's just try to get some points. Obviously, they're going to be all approximate since we only have x values that are multiples of 3. So -2, -5. All right, so I'm just going to go close to -3, but not quite get there. Okay, and then -1, -4, a little closer to the y-axis. 0, -3.4, so maybe somewhere around here. Okay, 5, 1, -3. 5, -2, so somewhere between 3 and 6 will be a -2. 13, -1, so somewhere between 12 and 15. And then 29, 0, so somewhere close to 30. Okay, so now I'm going to do my best at making this a smooth curve. So just knowing the domain of a logarithm, I know it's going to go, down towards, the range will go to -infinity on the left, and my x values will just kind of get closer and closer and closer to -3. So just drawing an arrow is important. And, you don't have to draw it all the way down the graph, but just showing that the graph would continue to go down infinitely. And then on the right side, drawing an arrow kind of pointing up and over, the x values will continue to get larger and the y values as well. I'm just going to label this the point 29, 0, and I'll label this the point 0, -3.1, oh, sorry, 0.415, approximately. Again, it didn't say you had to label. I have a table, so that's already, enough information, but just to kind of make sure we're really showing what they're asking. Okay, so we use an appropriate scale because what is not allowed to happen here is if, let's say, you didn't count by 3 or larger on the x-axis. You are never allowed to just extend, okay, maybe I can just extend the x-axis and no. They're giving you 10 boxes, which means that you need to fit what you need in the graph given. So if you need to draw a picture here of a graph that has an x-intercept and a y-intercept, and the x-intercept is 29, you have to count accordingly and use that appropriate scale so that you can fit that x-intercept on the grid provided. So we answered the first part of this question. The last part is really just asking you to describe that end behavior. So as x approaches -3, that's usually how we write it, like this. The behavior, what's the end doing? Y is going to, well, as x goes towards this asymptote, where is y going? It's going down to -infinity. As x approaches +infinity, which is the right side of this graph, where is y going? Let's go back up. Y is going also to +infinity. So the nice thing is here, they told you the x side of the end behavior, you had to fill in the right side. Okay, I hope this video was helpful for you to go through lesson 4. If you need to rewind, rewatch any part of it, please do. There are some practice questions attached to this lesson, and the answer key to those questions will be posted at the end of today. Thank you.